me.
Yes.
We're in YouTube now.
I am
can you
making the things live in YouTube.
So you can share my
Professor
screen.
Yes, yes. If you share, then we can have a look at that. Is open fine.
Is it okay for you?
The left something is coming. So okay.
Can you see my screen?
Yes, we are able to see, but it is not in the full presentation mode, I think, because is it in the full presentation mode?
Yeah, yeah. Sorry, I can try again. Sorry. I'm putting down full presentation, but if not, I can change to wait. Let me look. Let me change a little bit this. I think that now will be better. Just it's now. It's
Yes.
better now.
Yes, perfectly. It's perfect.
I'm taking a breakfast, a brief breakfast, just a coffee.
So how is it COVID in Chile? So it's the same questions nowadays.
Is the topic now? No.
Yeah.
We are starting again to go out, the commerce and everything. At the university, the courses are online. We're not going to the university. You know, little by little, the other activities are starting again. So we are afraid, of course, of the new wave of cases, you know. But it's more or less under control now, I would say, but we are not sure until, you know, we definitely will know the real number of death and everything. I don't know, in 1 more year when we can compare with a normal year, no? Not...
Okay. Okay, so you can start now. It's so maybe we can start now.
Yeah, sure.
Okay. Okay. So we heartily welcome Professor Eduardo Serpa and to all the participants of webinar on PDE and related topics. I request all the participants to store your question answer box. Now I request Ishendu Chaudhary to take the session forward.
Thank you, Prashanjit. We are honored to have Professor Eduardo Serpa with us today. Professor Serpa obtained a doctorate under Professor Jean-Michel Coron at the Université Paris-Sud, France in 2008. Currently, he is an associate professor in Institute for Mathematical and Computational Engineering, Pontificia Universidad Católica de Chile. He was the director of the joint PhD program in mathematics in Pontifical Catholic University of Valparaiso and Universidad Técnica Federico Santa Maria, Chile in 2019. His research areas are partial differential equation, control theory, inverse problem. He has been awarded the SIAM Activity Group on Control and System Theory Prize in 2015. Today, he will be speaking on control properties of a parabolic elliptic system. I hope you will enjoy the talk thoroughly. Professor Eduardo Serpa, It's over to you now.
Thank you. Thank you very much. Well, it's a real pleasure to be with you in India. You know, I've never been to India until now. Okay, so you know, this is the new possibilities that this whole situation, this situation offers to us. Okay, being able to talk to you even from my house here. I am in my son bedroom. You know. So it's a real pleasure. It's a new era to collaborate, you know, to get closer to each other. Well, I'm really thank you for the invitation, okay, and for the change of the usual time for the seminar. Because of the difference of time, it was very hard for me to do it at 3 as usual. So thank you for being that nice to change the time, okay. Well, it's as I said in the title and then the abstract for this talk, I'm talking about some parabolic elliptic systems, okay, more precisely on control properties, okay. So I know that this is a PDE seminar, so I will try to go very carefully in some definition and without entering in so many details, just to show you a little bit, a big picture on the different steps in this kind of problem. Okay, yeah. Well, this is a collaboration with Esteban Hernandez. Here is a PhD student in Chile and Valparaiso, in fact. Hugo Parada, who is a master student, yeah, with me in Santiago. Christophe Prier from Grenoble in France, and Kirsten Morris from Waterloo in Canada. Okay, I will present two aspects of this topic. So the first, well, I will just move forward. I will do a very short introduction of the subject. Okay, very short, 3 slides. Okay, then I will talk about a property called the null controllability, okay, of a system. During the talk, we will talk about one system coupling elliptic and parabolic equation, okay? And then the other topic is the stabilization, okay? So in this talk, I will present some null controllability results and some stabilization results, okay? For more or less the same system. It's a little different. In one case, we allowed some coefficient depending on x on the space variable, and the other one, there are coefficients which are constant, but it's the same kind of system. So let me start doing a very brief introduction just to say you what are the main concepts here. Okay, so we're starting very basic. Okay. So the controllability, what is the idea behind this concept, controllability? Let's think of this system. We have a glass here, okay, with water, for instance, okay, and the water is at a certain level. Opening this faucet, we want to fill the glass. That's our task, very basic, everyday task, okay. So what we do, well, just to start talking as in control theory, we have a system described by a variable called the state, and here the important point, the important variable is the height of the water, of the level of water in the glass. So that's the state. Then the control, we can act on this system by opening and closing this faucet, okay, to put or not put or not putting water in the glass. So we see the initial state, so the situation at the beginning where the level of the water is. We open the faucet and then we close it when we arrive to a final state, which is the target. Okay, this is the controllability. In fact, we have a system in an initial state. We do something, we do some control, and we arrive to a desired state. Okay, this is the topic of controllability. And for instance, here, even in this very simple example, we realize that there are some tasks that we can do and others that we can't. For instance, here, we cannot pass from a high level or a level to a lower level, okay, with this system. So there are some restrictions to obtain what we call the controllability, okay? So that's important to say what is the state of the system, what is the control, what we can do with that, okay? Even for this very simple example, that's the case. So the stabilization is very related problem, but it's a little different, okay, in the way how we solve it. For instance, here, you know, here we have two pictures. Here, the device that we have in our houses, okay, in the bathroom, okay, is you know, the same idea. Here is to keep the level of water at a certain position, okay. And the reason to doing that is that, well, doing this is very boring. And I opened the faucet, and then I got a WhatsApp, a cell phone call, and I forgot about what I was doing. So it's a real mess. Okay, so it's a very boring and can be difficult in some sense. Okay, so the idea is doing in automatic way. So and doing in automatic way is using technology, and technology is this. This is technology, you know. And so the idea is, well, to do a device in order to accomplish that task in an automatic way. So here I'm not opening or closing any faucet, okay? I just have implemented this. And we call it, in terms of control terminology, feedback control, okay, which acts already in automatic way. So depending only on the state, okay, depending on the state, the control is acting or not. Okay, here we already know how that works. Okay, this is the main concept. So let's put some equations here because we really like equations. Okay, so just to put some equation, let's think about this very basic example. Okay, the most simple control system. I'm just closing my window. Okay, thank you. Let's see here in the first equation, x dot equals to u and x at time 0 is equals to alpha. Okay, we have one ODE. X is not a vector, it's just a number, a real number. U is also a real number. So we will think of this equation as a system where x is the state that I want to control. U is to our disposal. I can choose as I want, okay? And alpha is the starting point, the initial state, okay? So a definition in this context is that we call this system controllable in time t if I can go for any initial state alpha to any final state beta, choosing in an appropriate way the control u. Okay, we said that we can do that in a time capital T. And here, of course, it's very easy because we can integrate that equation. It's just one equation, okay, and we can solve it explicitly. You give me any alpha, any beta, I define this control u here in red, okay, which is constant in time, okay. It's not the only one, there are many possibilities. This is one, the easiest, okay. And you solve your equation and you get that x on time capital T is beta, okay. So this system is said to be controllable in time t. Okay, for any initial state alpha, for any final state beta, I can find a control driving the system from alpha to beta. That's the idea of controllability in a very, very basic example. This is the first part of the talk, is about this property for some PDEs, okay? And the second part of the talk is about stabilization. So let's use the same simple example to introduce a little bit the idea, okay? So here again, we have the same system, okay? For instance, here we can see that if we do nothing, if we put control u equal to 0, we do nothing. So the solution is constant in time. It's just x equal to alpha for any time t, okay? And for instance, an idea in general is that introduce a control in such a way the solution x tends to 0 or to a fixed to an equilibrium point of the system, for instance. Okay. And so here we will say that this system is stabilizable if there exists a control, but a control depending only on the state, for instance. So a control u, which is kind of linear operator k, for instance, of the state x, such that if we put that control in the system, the solution is going to 0 when time goes to infinity. And here, for instance, let's go one step back. Here, when about controllability, you know, the control that you choose depends, of course, on the initial state. Here is very easy to see from depend on alpha, on beta, so depend on the initial and the final state, and here on the time. Okay, this is for controllability. For stabilization, we look for a control depending only on the state. Okay, so it doesn't matter what was the initial state. Okay, for instance, here in the definition, we say that we see that the system is called to be stabilizable if there is a control working for any alpha. So you choose a control, you choose your device to do your task in automatic way, and then for any initial state alpha, the system has to go to 0 when time goes to infinity. Here, of course, again, the system is very simple, and we can take u equals minus x, okay, depending very easily on the state. So we put that control on the system, and we get x dot equal to minus x, and the solution is nothing but alpha times exponential minus t. Of course, this is going to 0 for any alpha, so the system is stabilizable. Okay, and I will use the same basic system to introduce a difficulty appearing when we have a delay. So what that means? The same system as before, when we already put the control, so x dot equals to minus x starting from alpha. Well, the solution is alpha times exponential minus t, going to 0. So the system is, once we put it here, this is stable, okay? When the system is stable, we put a delay. We put a delay here. So instead of considering x dot equal to minus x, we consider x dot equal minus x of t minus capital T. Okay, and capital D, for instance, can be a known parameter or unknown. Okay, and that makes a lot of troubles. Okay, so the system, very simple, which was asymptotically stable in terms of dynamical system, can become unstable. For instance, here, that's the case if D is bigger than pi over 2. Okay, here we can look for solutions, and we get solution of the kind exponential of at at time cosinus or sinus beta t, okay, with alpha strictly positive. Okay, so to do that, we have to find the intersection of two curves here. Okay, and here in the right, in the drawing, there are some points called here C and D, which are very near from the y-axis, but they are positive. So that give you the solution alpha positive, so the system become unstable. And in fact, for PDE, that's because in the second part of the talk, I will show you some result concerning the elliptic parabolic system, okay, with a delay, okay? And for PDE, the situation is even worse because there are, in some cases, for hyperbolic system, for instance, some delay as small as you want, okay, making the system unstable. So the system that you already built in order to be stable with your control become unstable because of the delay. Okay, so it's a real trouble, okay, to take into account. So that was very roughly to introduce you the controllability, the stabilization topics, and also the troubles appearing with when you consider delay. Okay, and of course the delays are present in any application that you want to do. So it's a real trouble to consider. Okay, so let's talk about this non-controllability property. Okay, so we'll consider this system. We have a PDE system. We have y, which is the solution of a parabolic equation here. Okay, we have z, which is solution of an elliptic equation, and these two equations are coupled by the right-hand side, for instance. Okay, well, here we really, our approach really relies on the very particular form of this coupling. Okay, so we put for y, we need to add two boundary conditions. We put a control, which is in blue here, called u, okay, acting on the Dirichlet boundary condition for the parabolic equation on the left-hand side. We put on the right, we can put it on the right-hand side also, okay? It doesn't matter. And for C, we put it just the same kind of condition, but homogeneous Dirichlet condition for C, okay? So here we have a coupled system. So our state now will be the couple YZ, okay? And the control will be the function u. Still the function u is just for any t a real number, okay? We have some regularities of the coefficient, but during the talk I'm not talking about that, okay? It's not the main issue here, okay? And for this kind of system, there are some controls, even in this is in dimension 1, you know, the domain is just the boundary interval 0 L, okay, because that allows doing many particular things, okay. But in general, there are some results for this kind of system putting an internal control, okay, putting an internal, so a control acting on the right hand side of one of the equations, okay. Here, in order to put it on the boundary, we consider a problem in dimension 1. Okay, there are some paper of Felipe Chavez Silva and Sergio Guerrero in 2015, and there are 2 or 3 papers of Fernandez Cara, Juan Limaco, and Meneses. Okay, of course there are other, but this is more the closest to this work I am presenting now. Okay. So I'm just taking in the. I was checking the chat. If there is some question, I can read. Okay, so here we're interested in studying what is called the non-controllability. Okay, we introduced what was called the control, but in the very simple example, I mentioned that there are some tasks that you can do and other that you can't. For instance, in the glass of water, you cannot, for this particular system, you cannot go from a state with a higher level of water to another state with lower high level of water. Okay? Here, because of the equation, here's in the remark at the end, okay, because we know that the parabolic and the elliptic equation has regularizing effect, we cannot expect to reach any, for instance, any profile ZT or YT in L2, for instance, okay? So we introduce a new concept for this particular kind of system, for this parabolic, okay, that is called null controllability. What means that we can reach the state zero. From any initial state, we can reach the state zero by choosing in an appropriate way the control, of course, okay, and depending on the initial state. So the system is not controllable in some space X if we can, for any initial condition, we can find the boundary control U, driving the system from that initial condition to zero, okay? And so that's the property that we are studying here, okay? So we will do a trick, okay, in order to write our couplet system as a single equation, okay? And to do that, that's the reason that we are using a very particular structure of our system, that we introduce the following operator. So, okay, the operator capital F, taking a function G, putting as a right-hand side here in system 3 is an elliptic equation, put it as the right-hand side G, and the function and the operator capital F deliver the function Z, which is solution of this system 3. Okay, I'm not entering the details, but the operator F had very good properties. Okay, it's well defined, it's linear, continuous, it's self-adjoint, and we have very precise estimation of this continuity constant. Okay, by using the particular case that we're in dimension 1, we can explicit knowing of this coefficient. So with this operator, we can rewrite the system in order to get just a single equation, which is much easier, and the system becomes like that. Okay, I can show you again. Let me put it here. The system was for the parabolic system, we put here. So, you know, we can pass, we're using this operator capital F to a single equation, consider this C as f of y. Okay, let me show you here. So we get finally to 4, which is a system which is parabolic with this non-local operator f of gamma of y. Okay, so we put the control U here. And the precise definition, you know, when I introduced the null controllability of the system before, I just put the space X. Here, I will also mention the well-possessed of this system. So in order to state in a precise way the property that we can prove, here we can prove that the system is not controllable in space H-1 when you control with the boundary control U with regularity L2 in time. Okay, so that's the property, the non controllability here. Let me show you. So let's start talking a little bit about the well-possessed of the system, because it's I was told that this is mainly a PDE seminar with audience coming from different topics in PDE. So just to mention a little bit about the well-possessed. So we start with no control. Okay, we put here U, I put it in blue just to keep the color, but we put 0, so we have no control. I do it in a separate way because in general, we can, when we do control, we really need to get very precise, well-possessed results, okay, with kind of rough coefficient or rough boundary conditions, okay. For instance, for us, the control here is a function L20L, okay. So the regularity is not the usual regularity for the parabolic equation, for instance. That's the reason that at the end of the day, we get some result in the space H-1, okay. So in order to do that, we start first with no control. We put U equals to 0. So we have the system 5 here, okay. And we introduce just the operator A, which is the underlying spatial operator of the equation 5. So we put here at the right everything, okay? So the Laplacian of phi minus q phi plus f sub gamma of phi, okay? Again, this operator had very good properties, self-adjoint, dissipative, okay? So we can use general result on semigroup in order to prove that the system can give you a solution, okay? So we obtain finally, by using this general result, Hill-Yosida-Phillips theorem, that if y0 is in the domain of the operator, which here is H2 inter H01, and the right-hand side G has, well, this regularity, so then the solution is very regular, okay? Well, it's not very regular, but has the regularity of a strong solution in terms of semigroup, okay? The solution is going to be continuous in the domain of the operator. So this is the point A, the point B. There are going to be a point C and D, okay, which I show you here. Then, using this initial solution, which is what is called a strong solution in terms of semigroup, okay, until here we have a solution when we start with the initial state in H2 inter H01. Okay, but we decide to get solution, okay, with less regularity. So in order to do that, we can use some energy estimations, okay, and density arguments in order to get solutions when the initial state y0 is just H01, okay, not H2 inter H01, but just H01. Well, you can do it again using energy estimations. And in fact, that is very important that you can prove, you can get also that when you get the solution y, okay, yx at 0, so the trace of the derivative of y is a function in L2, okay? So the system has this additional regularity that's going to be used in a couple of slides forward, okay? So until here, we have some well-possessed results, okay, when there is no control, okay? Until here, the regularity needed for the initial data is H01, and the solution is going to be continuous in H01 and L2 H2, okay? So here's the point with the control appears. Okay, as I mentioned before, we really need a result with control in L2. Okay, so we define a solution, and this is a definition called by transposition. Okay, so we start. Let me show you here. We start with equation 5. Okay, we multiply by a test function. We integrate by parts. Okay. And at the end of the day, we see that appropriate definition of what is called a solution by transposition is a function y with in a less regular framework, here just L2 in time, L2 in space, such that for any h with that regularity, we get this equation. Okay, equation 7. Okay, and here there are a W appearing, and W is nothing but the solution of 8, what is called the adjoint equation. Okay, so this is our definition of solution for our system, or for our equation, for our heat equation with this non-local term. Okay, when the control is L2 in time. Okay, and the initial condition is H minus 1. Yeah. So next slide is just to mention that how we prove that the system has a solution. Okay. And we have here the theorem saying that if the initial data is H minus 1, the right-hand side G is L1 H minus 1. Okay. The control U is L2 in time, and the coefficient has regularity L infinity. Or okay. So there is a unique solution y, which is continuous in H-1 and also L2, L2. And there are, of course, the good estimation here of the norm involving in the results. Okay, so the idea, just to mention the idea, but this is very simple once you already get the solution of in a more regular framework. Okay, fix Y0, G and U, because they are the data of our problem. Y0, G, U. Okay, and we will see H as a variable. And we will go to previous slide, and the right-hand side of 7, okay, the right-hand side will define a linear bounded functional from L2, L2 to R. Let me show you. Here, we have 7. We have the right-hand side of 7 here, okay? The right-hand side, once we have fixed Y0, G, and U, okay, the right-hand side depends on W, and W depends linearly of H, okay? So we see here the right-hand side as a function of H. So the idea, okay, is proving that this is a linear bounded functional from L2 to R, and then the Ries representation theorem tells you that, the right-hand side, okay, as defined a functional from L2, L2 to R, will have a representant, okay, and that element from L2, L2 is gonna be Y, okay. Yeah, so that gives you the regularity L2, L2, and then by doing estimation of energies, you can recover that the solution is not only L2, L2, but continuous H-1. And that regularity is very important because for your control problem, we want to start with an initial condition in H-1, and we want to define a trajectory of our system, which is continuous in that space H-1. Okay, so this our theorem with Esteban Hernandez and Christophe Prieur is that one, the system 4 is null controllable in that space H-1 with control in L2. Okay, and of course I put it like a corollary here. Okay, but just saying that once we get the control of the system of the single equation with a non-local term, that's equivalent to get the control result for the original parabolic elliptic system. Okay, I just mentioned that because just to not forget that we start with this system coupling a parabolic and elliptic equation. I'm not going so much in the details, but in order to give you the idea, okay, the general idea of this kind of result, at least for parabolic equations, okay, when controlling parabolic equation, I will show you how to prove that. Okay, so we use here what is called an observability inequality. We have the equation 9, which is the same as before. We have the parabolic equation with this operator F here in red. We have the control U, okay? And in fact, I'm not mentioning that, but using a method called the Kahneman estimates, okay, we can prove the inequality, what is in blue here, okay? And W, where W is the solution of the equation 11, which is very similar to the previous adjoint equation used when defining the transposition solution. It's not exactly the same because before there were not initial state. Here we have WT, okay, but it's more or less the only difference, okay. So by using these Kahneman estimates or in other contexts, we can use energy estimations. We can get some estimates as 10, what is called here observability inequality, okay. And so I will show you a little bit how to use this inequality 10 in order to prove our control result, okay. So we will consider, so we assume from now on that we already have proved this inequality 10, which is in blue here, okay, by using a Kahneman estimates approach, which is very technical, but is nowadays very classic for this kind of control problem for parabolic and on another system also, of course. So we consider the following functional, okay? We fix epsilon, we define the functional J epsilon going from H01 to R, given by, here we have the L2 norm of the trace of the derivative of the solution W. We have here a dual term between the initial state Y0 and W, okay? And we have to add here a norm of the solution WT, okay? So this is a lemma, a technical lemma. This functional is continuous, strictly convex, and coercive, okay? So in that way, J epsilon has a unique minimum, okay? That's the way. So here, this functional is well defined because we pick a WT in H01, okay? We solve equation 11, okay? And we get a solution which is continuous in H01 because of our first result on well posended with no control. Okay, you know, when there is no control, the regularity is higher, can be in H01. That's the regularity that we're using here. Okay, so this is the functional. So we can prove in a next step that the minimum, okay, sorry, the minimum of this functional J epsilon can give you not a control driving the system to zero, but driving the system near zero, okay? So here, that's what I mean. Given this epsilon fix, okay, we pick the minimum, which is called WT hat epsilon, okay, many names. So we pick it, okay, we pick the minimum. We find the W hat epsilon, the solution with that initial state. So we pick the minimum, we put it here as an initial condition in time capital T and 11. We recover the solution, what we call W epsilon hat. Okay, and we can prove that for that solution, taking the trace of the derivative, it is a function in L2, okay? The regularity here we have already proved, as I mentioned, when we defined what was a solution by transposition just before that, okay? And we can prove that that control, explicit control, so that gives you an idea how to find numerically, for instance, even if numerically is very exposed that problem, but that gives you an idea how to find it, okay? Is a control such that the solution satisfies that the norm of y at capital T in the space H-1 is less than epsilon. So we're near, is epsilon is small, we're near from zero, okay? So that's the first step. And then a second step, okay, is that you, let's read that. So for any epsilon, we have a control, what is called an approximate control. Approximate because we are not getting to zero, we are getting near zero, very close to zero. Okay, so for a sequence of epsilon going to zero, we define the control U epsilon. Okay, we can prove that this sequence of control, okay, weakly converge in L2 to a control U, and that's the control that drives the solution to zero. Okay, so here in other content you can also do an approach like this, but what is crucial here in order to get that, you get this weakly convergence, okay, or equivalently you get that the norm of U epsilon in L2 is bounded. Here is when you use the observability inequality in blue, okay? Let me show you how a little bit, okay? So as I mentioned here, I put the key point is that the sequence is uniformly bounded in L2, the sequence of controls, okay? So to do that, as we have that WT hat is the minimum, well, the value of the functional is less than the functional at 0, which is 0. Because of the form of the functional, we can get 15, okay? 15 here, so the term minus epsilon, we just neglect it, it's negative, okay? And here we do a Cauchy-Schwarz inequality, okay? We just do a Cauchy-Schwarz inequality, getting that, okay? I'm going forward. So the previous inequality is the same as here, the first line, the first equation here, okay? And in blue, I put again the observability inequality, and we can see here that that gives us exactly what we need, because we can bound by below this term here by using the inequality in blue, and we get here 16. And you know, remember, this is exactly the control U epsilon. So that gives you that the control U epsilon are uniformly bounded. There is no epsilon here at the right-hand side of 16. They're uniformly bounded, and so you can take a subsequence converging weakly, okay? And you can prove that the limit, okay, the limit is in fact a null control driving the system from your initial data to 0. So this is just to put again the result. So this is more or less the idea how to prove it, okay? But I repeat, I didn't mention any details about an important part of the work, or it's about getting the Kahneman inequality, okay? Of course, this follow very closely what you can do for the heat equation. Here, in fact, you can do step by step almost everything as in the heat equation when this term in red is not present, okay? In fact, the novelty of that work is verifying that everything worked well, okay? Everything what's already known for the heat equation worked well if you put this operator F here in red. So that was for the non-controllability of the system. Now we are considering the same system, but with constant coefficients, and from a perspective of the controllability. Okay, from in terms of there is a, okay. And so the system is the same, but I put the constant coefficients here. Okay, so we have, well, I just changed the names. Okay, sorry, but the files are from different papers, so that's the reason. So the system is a parabolic equation. Now U is the state is not the control. Sorry for that. The control is H here, and I just realized I put the control in the right-hand side now, not in the left-hand side. But you can do exactly the same if the control H is acting on x equal to L or x equal to 0. Okay, so you have the parabolic equation U coupled to the right-hand side with an elliptic equation V. Okay, and in fact we will do the same, and we will rewrite the system as a single parabolic equation with a non-local operator in the right-hand side. Okay, here an important property of the system is that when the control is 0, when you do nothing, you know, remember at the very first, when we start the talk, we mentioned a very simple example where if we put no control, the solution was constant in time. Okay, and we wanted to change that situation. Here, when no control is applied, the system can be unstable if the coefficients involved here, alpha, beta, lambda, gamma, okay, and the domain L, the length of the domain L, if this coefficient satisfies this condition, okay, the system becomes unstable when no control is applied. So there will be some solutions, at least for some initial data. for which the energy is going to infinity. Okay, so we want to forbid that, to change that configuration, to change that property by introducing the control H. And here, as I mentioned in the example, we're not only considering a control H, but we're considering a delay D. No, in fact, well, I'm just taking a question here in the chat. Is there any specific reason to prove the null controllability via the kind of approximate controllability? In fact, you can do it directly. Okay, no, in fact, you can. I found that for people seeing this for the first time was a little clear, but what was clear. But no, you can, in fact, you can do in duality arguments, or even introducing other kind of functional, you can prove it directly without passing by approximate controllability results. So, so here, I was telling you, the idea is to introduce now a control H, taking care of the delay D. Okay, we assume that we know exactly the value of the delay D. Okay, taking into account the delay D, and of course, taking a situation where the system is unstable and making it stable. Okay. And
there is another question in the question answer box.
There is a box question and answer, but I can see the questions.
I can read it to you. So it's written, what happens if we put control in the second component of the solution?
In a different component?
Yes, in the null controllability portion. So you have put a control on Y, I think. So I think he's asking that if I put a control on other component.
Yeah, that's very good point, because in fact we haven't tried very hard, but the problems are different here. For instance, here, of course, if your control is on the elliptic part, so you can use directly the same operator as I mentioned before. Okay, of course. So there are things changing. For let me remember what was the situation. For the controllability part, we can do more or less the same in a different way, but for the stabilization part is different. Okay, we don't have the reason in any case, in fact, but just thinking about the difficulties, I think that situation is a new problem. It's not solved. I think that the controllability was closer than getting a positive answer. Okay.
So for controllability also, how it is clear for controllability purpose also, means if you put a control on the second component.
If you put another, or you change. If you change, well, I was mentioning, if you put another control, well, the situation is easier. Well, you can even choose it 0, of course. But if for the, let me remember, well, for the controllability, yeah, because in fact there is another method to consider the controllability bar, which works here in the case of constant coefficient, what is called the moment method, which is an spectral method to prove also controllability results. And using that method, you can obtain it, in fact, but not with the, that's true. With the Kahneman estimate, I'm not sure, in fact. But with the other approach, you can do this more or less the same, but you really need the coefficient to be constant. I think that there is another question, but I can't see. I don't know why. I just see the chat, but not the questions.
In question answer box, another thing is there. Will you later consider the issue of null controllability for nonlinear system?
Yeah. That's also a good point. Here, for instance, if we put in the previous topic about controllability, if we put a nonlinearity on the parabolic equation, everything can be done in a similar way for the linearized system. Okay, and then you can use it with a fixed point argument or the inversion theorem in order to get the same result for the original nonlinear system. Okay, if you put it that nonlinearity on the elliptic, that give you more troubles because that change the way you are introducing the elliptic equation into the parabolic one. Okay, that affect you more heavily. Okay, but if the nonlinearity is in the parabolic equation, everything can be done. You can get, in fact, the result for that case. Okay, nonlinear with nonlinearity. Okay, so here we are following for the stabilization part the same approach as Christophe Prieur and Emmanuel Trellat they did it for the heat equation. Again, as I told you in the previous non-controllability part, okay, we basically have to study that everything works as for the heat equation, even you to put this non-local operator F. Okay, here's more or less the same spirit. Well, and this approach that we're using here was used, okay, also by Bresch-Pietri, Christophe Prieur, and Emmanuel Trellat, okay, for a finite dimensional system in a paper with Patricio Guzman and Swan Marx for a parabolic system of higher order. Okay, so and the situation. So I mentioned that when you put no control, it's I have 5 minutes. Is that right? No.
It's okay. You can continue.
For 1 more hour? No, I don't think so. No, just give me a couple of more minutes, please. But not
sure.
too much.
Yes.
Okay,
Okay.
I'm going. Okay, so the system is unstable. So the reason is then when you compute the eigenvalues, you find this explicit formula. That's the reason why we really need to be in the constant coefficient case. And you can, in fact, when don't control is applied, you can find explicitly the solution U and V. Okay, and the solution are here. Okay, the eigenstates are sinus functions. Okay, and the dependency here is on the sigma n. And of course, here the problem is when there are some positive sigma n. Okay, so the system will be unstable. As again, we define the same operator f of gamma. Okay, in order to write the coupling system as a single equation here on the bottom, a single equation, the parabolic equation for u with the coupling, okay, with this non-local operator f, okay, where you put a control h on the right Dirichlet boundary condition, okay. And of course, I didn't mention in the first part, but the elliptic part is just defined by u and this operator f of gamma. Okay, so we just make a change of variable with the goal of putting the control inside your domain. Okay, I'm going a little faster now. So this is the equation that you get for W. So in red here, you get the equation for W. You get that the control appears at the right-hand side, but also you get the derivative of your control appearing in the right-hand side of the system. Okay, the operator A is the operator that we already know that appears here. Okay, the operator A is self-adjoint with a compact inverse, so you can get the eigenvalues. We know it explicitly, in fact. Okay, and the eigenfunction, which is this sinus function, and you can so write the solution W as a series of this kind of combination. Okay, so as the system is linear, well, if it's not linear, you have to add here another term. Okay, but you can manage that. You see coordinate by coordinate, and you got this this equation for the WG. J, sorry, for Wj, you get this equation, okay? I'm going a little bit faster. And the idea is that you look at the coordinate, and for instance, if you got a combination of coefficients such that you get n positive eigenvalues, okay, you have that the system is unstable because there exists an n-dimensional subspace of your space L2 in which your system is unstable, okay? So we look carefully to that unstable part, okay, which is represented here by the state xn, where we have add the control as being part of the state, but the new control is in fact the derivative of the previous control h, okay? So here we get a system, here in the bottom, you get a system which is, when there is no control, the system is unstable, okay? So the idea is to put a control, which is called here new, a control new in order to stabilize that, okay? And this is possible by means of our method because this is a finite dimensional system, okay? That's the way that we take care of the instability. So putting all the positive eigenvalues together, looking at that coordinates and introducing a control, okay? But the second problem here was there is a delay. So in order to deal with the delay, we make another change of variable, okay, what is called the Arnstein's transformation, going from X, the original state, to Z, okay, by using this transformation. And this is very nice because you get the system in red for C. So the system in red has no delay. So the delay D present in the system for X, when you look at in the system for C, you get that there is a matrix here depending on the number D, but there is no delay in the control. So you can apply any, for instance, here, the pole placement method, which is a method in finite dimension in order to move, okay, in order to move the eigenvalues of your system in finite dimension. Here we can check that when you look at the system for Cn or for Xn, the system is controllable. I'm not entering the details here, but you can prove that the system is controllable. So you can find that control in order that you can stabilize the finite dimensional part of your system. Here I'm just mentioning that in fact you can get a function, a Lyapunov function, okay, describing the right behavior of the system when you already put the control. There is a Lyapunov function giving you the decreasing of the energy, so giving you a way to manage the unstable finite dimensional part, okay, which is the implicit function for your control nu, okay, where this matrix Kn can be proved to exist, you can find it, okay? And so you stabilize the system in red, and in that way, you finally stabilize the system for X by defining this control nu here, okay? And in fact, you can use a Lyapunov function not only for the finite dimensional part, but for the whole system, okay? This Lyapunov function Vd has the final dimensional part, but has also here at the end a term depending on the whole solution of your system. And here the structure of the control for nu is a control as if the system has no delay, so a classical control, plus a term depending on the control in the past. Is implicitly defined, okay, but you can in fact write it in an explicit way depending on your state. So at the end of the day, well, sorry, it was very fast in the last slides. So at the end of the day, you get the result that in fact you can build this feedback control law such that for any D, well, for any D, you build this feedback law, and for any combination of coefficients, okay, given any combination of the coefficient, even given any d, you can design the control stabilizing the system in this sense. And the fact that when you put the control, the solution in the appropriate norms goes exponentially fast to 0. Okay, we have c exponential minus mu t, the norm of the initial condition. And well, just to show you that you can make some simulations. Okay, here we use some MATLAB tools. Okay, for some configuration where there is only one positive eigenvalue. This is very small, 0.0007, but the system is still unstable in that situation, and you can build the control, the feedback control that I mentioned, applying the R state transformation and also the pole placement method. And well, thank you for your attention. Thank you very much, and sorry for having 3 more minutes than I was allowed. Thank you.
Shishendu.
Yes. Thank you very much, Professor Eduardo Serpa, for such a lucid talk. We have received some questions from the participants. I am conveying to you on their behalf, and I will also have some questions.
Sure. Yeah, well, in the chat, Jean-Michel, hi, Jean-Michel, how are you? Jean-Michel Coron asked a question about the robustness with respect to the value of the constant d. Okay. Well, in fact, you know, the system is robust with respect to d. We didn't put any precise estimation of that fact, but everything in the construction is robust with respect to d. You see in the Lyapunov function and the final dimensional part, and everything works fine. We should ask maybe some. We didn't put any comment about this in the. Well, it's not submitted yet, that part. Okay, but yeah, it's a good point to add. Okay, well, for the general, for all the people, well, the point is that maybe you find a feedback control for a particular value of d, and then you change a little bit that value of d, and everything got nuts. That's not at all good. Okay, this is not the case here. There is this robustness with respect to the value of the delay d.
Okay. So there is another.
I can see the. I don't know where.
It is in the question answer box.
Yeah,
so
I click on that, but
it's written, does the decay rate mu depend on d?
The decay. Well, you know, for any delay d, okay, you give me a delay, I can build a control going very fast to 0. Okay, because in fact, you know, that depends on how many eigenvalues I consider, because of course I am very worried about moving the unstable eigenvalues, but I can also move the stable eigenvalues just to make the system going faster to 0. So if you want a given decay rate, I consider how many eigenvalues I have to move, and then I can do it with no problem. Of course, in terms of cost on everything, it can be harder, but I can do it, okay, theoretically.
So the mu doesn't depend on d, that's what you are saying? The decay rate doesn't depend on d?
Well, you know, for any, what happens is that you give me a d and can build you a feedback load, okay, such that the system is going to 0 with the decay rate that you also give me at the beginning. Okay, you give me a decay rate mu, a delay d. I can build everything that in terms to get this exponential decay at that rate. Okay,
Okay. So that means it is stabilizable with any decay rate, whatever you give.
For any, yeah, but of course with different controls. Sure.
Okay. Okay. So there is another questions in the null controllability part. It is written, how can we conclude that the Z at the time level T will be 0? Because you have shown only Y. So from where, how you show that it is in Z will be also 0 at time level?
Yeah, sure. Yeah, well, I didn't put the condition that, you know, the coefficient has been chosen such that, for instance, there is no other solution associated to the right-hand side 0. So maybe I can show you here. Well, let me show you here. Okay, so for instance, let's see here the elliptic equation. Okay, if for a capital T, sorry, you have the yt is already 0. So the elliptic equation at time capital T gives you the solution of minus Laplacian plus gamma c equal to 0. And so in order to have the solution 0, you have to impose some condition on the coefficient gamma in such a way when you put y equal to 0, the only solution is the solution 0. Of course, yeah. If, for instance, you allow the gamma be very negative, so you can get, for instance, a eigen solution of the Laplacian, well, there is trouble. You cannot be sure that the elliptic solution is going to be 0. But with some condition on the coefficient gamma, you can be sure that if y at time capital T, sorry, is 0, the only solution for C, for the elliptic part, is also 0. But sure, there is an issue there. You have to impose that conditions on the coefficient in order to avoid having multiple solutions, for instance.
So there is a comment that basically when you reduce two systems in a single equation, we get a solution operator on right hand side. Can we use more general, say, nonlinear operator with some specific properties?
Yeah. For instance, what I was mentioning during the talk, if you can consider the nonlinear term in the parabolic equation, for instance. Okay.
Okay.
Yeah.
So, and another thing is asked that what kind of controllability results do we expect for our parabolic elliptic system when the space domain is higher than 1? So in multi-dimensional.
Well, in the multidimensional case, well, you know, there are also the same kind of result in terms of getting null controllability result, but with an internal control. So not a control acting on the boundary, but that there is the result that I know, but in the control on the putting here, for instance, instead of just C, putting C plus a control H. Okay, so a control distributed and acted on a subdomain of the original domain. That's the result by, for instance, here Chavez Guerrero and also Fernandez Caralima Comeneses. In those papers, they consider that in higher dimensions. Okay, with an internal control.
Okay. So I request if participants has any other questions, they can ask. Otherwise, I will ask 2 questions.
Sure. Let's go.
Okay. So first of all is the system you consider when you have a parabolic and elliptic one. So instead of parabolic and elliptic, is there a controllability for this system has a connection with 2 parabolic system?
2 parabolic, yeah. In fact, in the paper that I mentioned of Guerrero and Chavez Silva, their strategy was to consider 2 parabolic, okay, but in one of the parabolic equation, in the terms, for instance, y of t, in the time derivative, you put a coefficient epsilon, which is very, very small. and you consider that the system, instead of parabolic elliptic, you consider parabolic parabolic, in one of those a coefficient very small, and then you prove that you can control that in a way that is, let's say, independent of the epsilon, so you can pass to the limit. And so that's another strategy, okay, to do that.
So if you prove the controllability for the epsilon dependent problem, then it is uniform with respect to epsilon, and you pass to the limit, and you will able to
you have to prove that. You have to prove that. Sure. They have done that.
But is there anything, because I want to know for this one, parabolic and elliptic, suppose you have a negative result for a parabolic and elliptic system, will you have a hope that for the evolution, parabolic will also have this kind of negative thing? Means this is the approach you are selling, that from two parabolic, you are coming back to one parabolic and elliptic as a uniform limit if you go. But if you have some kind of a negative result for a parabolic and elliptic system, can we conclude something about the parabolic model?
That's a very good question. In fact, well, there is a very interesting phenomenon appearing for PDEs, when concerning that the situation can dramatically change when you put one coefficient equal to 0, for instance. Okay, there is an approach in finite dimension to study, for instance, the stabilization for a system. You can use, for instance, when you have some parameter very small, you can use the limit case when epsilon, let's say, is equal to 0, in order to stabilize the system where epsilon is not 0. But that kind of phenomena cannot be doing in the same general way for PDEs. I don't know in the parabolic situation, but for the hyperbolic situation, I have worked on that with Christophe Prieur, on some even hyperbolic ODE system where you cannot be sure of the general situation just doing that. This singular perturbation methods that work very nicely for in finite dimension. When you consider PDEs, there are some unexpected situation appearing, so you cannot be sure of that.
Okay, so this doesn't give you anything, in general, it doesn't conclude anything about the parabolic model. That's what you're saying.
I would say that, of course, I'm not sure.
Okay. So another thing is that the non-linearity, you tell that, is it any non-linearity, or you have to put some kind of a global ellipsis? Those kind of non-linearity you have to put, or it will work for any kind of non-linearity?
No. Of course, you have to consider some non-linearity. For instance, for the heat equation, I don't remember the details, but for the linear heat equation, for the heat equation, you can consider some non-linearities. There is a limit; you cannot put everything. But here, the situation is going to be exactly the same. In fact, okay. So the same limitations will appear when doing the same with this, adding some non-linearity to this parabolic elliptic system. But yeah, I don't remember. But the non-linearity you have to be able to manage them with, for instance, your Kahneman estimates, and yeah, there is a limit. You cannot do everything. Okay, but I don't remember very well the kind of limit for the non-linearity.
So in your proof of the stabilization, essentially you define h dt when you have the delay with a d. So suppose you have a stabilization result with a h of t without delay. So is it obvious that it will be with a delay also this will work? Only the transformation you use in between, there is one transformation which reduces the problem from delay to without delay equations, right? Because of that, that transformation. So my question is, suppose you have shown the result corresponding problem with a function and the control as a h of t, there is no delay, and you have shown some result corresponding to stabilization. So will it also holds in the case of delay because of the transformation you mentioned that? Is it obvious or it's something non-trivial?
I'm not sure that I captured well, but well, in
The
some cases you define your control with no delay. Okay, you build your feedback loop, everything is working very nicely. But for instance, for the wave equation, there are some explicit example where you are in that situation that everything works well, and you add a very small, as small as you want, delay, and the control is not working anymore. Okay.
Okay.
So you have to be very careful. That I know that some example for hyperbolic system, okay, for wave equation and beam equations, not for parabolic one, but you have to be alert of that. It's not sure.
Okay. I think there is one question already in the case that what happens in the case of parabolic and hyperbolic wave equation?
Yeah,
So,
I don't know.
okay.
I don't know what happened here, but you know, for parabolic, hyperbolic, yeah, no, I'm not sure. I don't know. I don't know. I don't know an example of a paper. Just to tell you, no.
And the last one is that the control regularity, I think as you have differentiated that HD, so you need some kind of H1 regularity on that H, right?
Yeah.
So if
in fact, yeah, but you know, at the end of the day, your control H is defined. Well, I didn't mention anything about the well-possessed of the closed loop system for the stabilization part. Okay, I didn't mention in the talk, but in the paper we have the proof of that. Finally, your feedback, your control H depends on the solution itself. Okay, so that's the way you get the right regularity of the finally of everything. Okay, because of course when you say the boundary control it is H1, so maybe it doesn't match the regularity that you expect for the state and everything, but you can do it for the closed loop system. In fact, you have to prove again a well-possessed result for the control that you are designing. Okay, so you cannot use a general result on well-possessed because it's not that you give a control, a function, and then you get a solution. That solution depends strongly, it's part of the control, in fact, in some way.
And this is the last one, that this control you construct for the null controllability. So in that case, can we get a feedback control for the null controllability?
Well, this is well, I had never done that. Okay, but for instance here, which is Michel is here for the heat equation. You can use, in fact, some feedback control in the other direction. Maybe you can find some feedback controls stabilizing the system and push a little bit in order to prove that that kind of control give you also some null controllability results. Okay, so passing some way to the limit, and so driving the system to zero by means of control defined in a feedback closed manner, and then to go to a control driving exactly zero in a given time t. That's that the result that I know. Michel done with for hyperbolic and some parabolic equations in dimension 1.
So thank you, Professor Sherpa, for this making this session successful. We hope to get your participation in future talks as well. Prosenjit, it is over to you now.
Thank you, Professor Sherpa. And I hope all the participants has thoroughly enjoyed your talk. And we meet in another 2 days for Emil Widman's talk on compressible Euler equation. Now, I request all the participants to leave the platform, and a lot of thanks to Professor Sherpa. Bye
Bye
bye.
bye. Thank you very much. Take care.
Thank you. Bye. Okay, I'm ending the meeting.
Okay.